Hello, it's week 11. We're doing chapter 5.4 and 6.1. So there's not really a whole lot new in chapter 5, section 5.4. It's on right triangle trigonometry, but I'll go over like 4 different problems to show you the types of problems that might come up. Really not great problems written in the exercises for these either, so sorry about that, but that's the book. Okay, so here they're saying find an exact value for pi over 4. Okay, so pi over 4 would be something like that, where that's theta, right? So theta is pi over 4, but we also know that that's 45 degrees. Okay? All right. So it might say find an exact value, or it might say find all the trigonometric values, meaning sine, cosine, tan, cotan, secant, and cosecant, because it didn't say what to do here. So when it says find an exact value, they're going to be asking for all of them. Okay, so what we know is that this is a 45, 45, 90 triangle, and so each side is rad 2 over 2. That's from our special triangles. Okay, so sine theta is opposite over hypotenuse, and the hypotenuse, of course, is 1. So it's rad 2 over 2. And cosine theta is adjacent over 1, so it's rad 2 over 2. And tan theta is opposite over adjacent, so that's 1. Right? Because it's rad 2 over 2 over rad 2 over 2, anything over itself. So cotan theta says flip this fraction upside down. So it's 1 over 1, so it's still 1 over 1, just 1. Then secant theta says flip this fraction upside down. So that's 2 over rad 2, and we have to flip that upside down, right? So, so that's already flipped upside down. So we have to rationalize the denominator. So we're going to rationalize by multiplying by rad 2 over 2, and we get 2 rad 2 over 2, which is just rad 2. So that's rad 2. And then cosecant theta is also rad 2. Okay, so we've answered the question. The exact value for pi over 4 for all 6 trigonometric functions is that thing. Okay, how about if they ask a question like this? If the cosecant of pi over 6 is 2, find the secant of pi over 3. Okay, so what I'm going to do is first figure out what information they're giving me here. So I'm going to do that by, again, sketching pi over 6. Okay, pi over 6 is pretty small because it's only a sixth of the way around to 180, right, to pi. So a sixth of the way is only about that big. But I'm not going to draw it that small because then I can't write in here, right, if I make a triangle that small. So I'm always making my triangles pretty much the same size. They pretty much all look like they're 45 degrees, right, because I don't really care. I'm just trying to figure out what the pieces are. I'm not really trying to be accurate in my sketch. My sketch is to help me. So theta is pi over 6, which is also 30 degrees, right? So that means this is 30 degrees. And we know that opposite the 30-degree angle is 1/2. Opposite the 60-degree angle, which would be here, is 1/2 rad 3, which is rad 3 over 2, right? It's whatever is opposite the 30 times rad 3. And then this is our 1, okay? So in this case, they're not asking me to find all of these. They're only asking me to find the secant of pi over 3. Well, if this is pi over 6 and it's 30 degrees, then this is pi over 3, it's 60 degrees. So the secant of this angle right here, right? This is the angle I'm dealing with, okay? So the secant of this angle is secant of any angle theta is 1 over cosine theta, right? So it's take the cosine and flip it upside down. So let's find the cosine of pi over 3, okay? In this situation, cosine is adjacent over hypotenuse. So the cosine is 1 over 2 over 1, so it's just 1 over 2. So that means the secant must be 2 also. Okay, and by the way, the cosecant is also 2 because cosecant of this angle here is opposite and hypotenuse. It's hypotenuse over opposite, so it's 2, right? Flip that upside down. Okay, so that kind of should make sense because it's secant and cosecant, and secants and cosecants are the complements of each other, right? So hopefully that came across in another video, or you've seen that somewhere before, hopefully, I don't know. Okay, all right, how about they ask us something like this? We have a right triangle, and one of the angles is pi over 3. So we have a right triangle, right? We don't know what kind of right triangle yet, but then they tell us one of the angles is pi over 3. Okay, so maybe it's this angle right here is pi over 3. Okay, and they also tell me that the hypotenuse, right, that's this guy, is 20. Okay, and they say find all the other angles and sides. That's also another way of saying solve the triangle. Okay, so just know that language because it could come up somewhere else, like in other textbooks or something. They might just give you a piece of information, like even this information up here, and say solve the triangle, and that means find all the angles and the sides, and we did that. We didn't write it down, but we did. We know all these angles are 45 degrees and 90, so we know all the angles, and we know the value of the sides. Okay, so here we have pi over 3, right? So that's the angle pi over 3, which is also, what value is that? Pi over 3 is 60 degrees, right? So if this is 60, then this one must be 30 degrees. This is the 30, 60, 90 triangle. So think about it again. Opposite the 30 is always 1/2. It's 1/2, right? Like up here, oops, sorry, here's my 30, 60, 90. Opposite the 30 is always 1/2. It's 1/2 of the hypotenuse or the radius, right? So if this was 10, this would be 5. If this was 20, this is going to be 10. So opposite the 30 is 10. And then opposite the 60, just like I said it before, it's the thing opposite the 30 times rad 3, or it's the 1/2 times rad 3. So it's the thing opposite the 30, or the piece that was 1/2 times rad 3. So it's 10 rad 3. So I have now labeled all the angles and all the sides. I know their values. Okay, if you want to be complete, maybe you would also say this is equal to pi over 6 because we had some in radians, so we might as well put the rest in radians. And that's it. We've solved that triangle. Okay. Next, we're going to talk about one more problem related to right triangle trig, section 4.5. And that is a real life problem, okay? So they tell us that we have a building, okay? So here's the side of my building, right? Here's a whole bunch of windows in my building, whatever, blah, 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 okay? Here's a door. Okay, so there's my building. And usually most buildings rest 90 degrees to the ground. Okay, so there's the ground. And they say, we want to know about a ladder that's leaning against this building. Okay, so there's a ladder leaning against the building. And the ladder is what we want to find the length of. But what we know is that it's reaching to one of the windows, which is 50 feet above the ground. Okay, so here is the ladder. Okay, so I'm not going to draw it like a ladder, but that's the ladder. Okay, so here's 90 degrees, and it's 50 feet up. So this distance here is 50. Okay, we know that. Okay, and it's making an angle with the ground. Okay, this is a really strange way to label an angle, but we're going to figure out what this means. It's making an angle with the ground right here of 5 pi over 12. Now you can figure this out in a lot of different ways, right? You can think about this in different ways. So let's remember what we're looking for. We're trying to figure out what the length of the ladder has to be, okay, in order to make 5 pi degrees, radian, sorry, not degrees, 5 pi over 12 angle measure from the ground 50 feet up. Okay, looking for the length of the ladder to the nearest foot. Okay, so let's think about what we already know. Okay, we know that in this right triangle, we're looking for the hypotenuse. And they've given me this angle measure. They gave it to me in radians, which is a little funky, but they gave it to me and so I can use it. And in relation to this angle, they gave me the opposite. So I have the opposite and the hypotenuse working in this problem. What am I going to use? Opposite and hypotenuse, or hypotenuse and opposite? That's the sine function. So we're going to say sine of 5 pi over 12, or I can call it theta just to make it easier, is equal to opposite over hypotenuse. So I have that. Okay, now I can't just throw the sine away. That's related to this. And because it's in radians, that's a little funky. So the first thing we're going to do is work through that radian piece. Okay, all right. What I know is that, well, okay, again, you can do this in a number of ways. You can just substitute 180 in here, but another thing that you can think about, and if this confuses you, don't worry about it. Just substitute 180 in there, and you can reduce and multiply, or multiply and reduce, whichever way makes sense for you. Here's what I'm thinking. I'm thinking I don't know twelfths, but what I do know is sixths. So if it were 5 pi over 6, right, then my reference angle for that particular angle would be pi over 6, and pi over 6 is 30 degrees, right? We've done this a million times already, and you should have it written down someplace, right? That pi over 6 is 30 degrees. Okay, so that means 5 pi over 12 would have a reference angle of pi over 12, and it's going to be half of this, 15 degrees. Okay, you should still get that if you multiplied 5 times 180 and divided by 12, or you did 180 divided by 12 and then multiplied by 5. Either way, you should have gotten that it was 15 degrees. So now I'm going to rewrite this sine function as sine of 5 pi over 12 equals 50 over x, as sine of 15 degrees equals 50 over x. So now I'm in degrees. Okay, so now I can take out my calculator. Remember, we always go at least 4 places when we're dealing with trig functions. So I can take out my calculator and I can do sine of 15. Okay, so that's 0.2588 is equal to 50 over x. I'm going to multiply both sides by x, so 0.2588x is equal to 50. Then I'm going to divide both sides by 0.2588, and x is approximately 193.2 feet. So to the nearest foot, there's my answer. Okay, now you might think, wow, that's a really long ladder just to get up 50 feet. But this is a really small angle, right? 15 degrees is really small, so this is way far away from that building, right? My picture is nowhere near accurate, okay? All right, that makes sense. And that's pretty much what you need to know for section 5.4. Okay, now we're moving on to section 6.1. In section 6.1 is about graphs of sine and cosine functions. Okay, sometimes these are called sine and cosine curves. And sine and cosine curves are very, very famous. They show up all over the place. Like, for instance, sound waves run on sine curves. And a cosine curve is really just an adjustment of the sine curve. So we're going to talk about that a little bit. There is an older video which does this in a really good way. It explains most of this stuff really well. And then at the end of the video, if you wanted to stay on for the last minute and a half, I show you my doggies. So if you want to see some cute dogs, you can stay on for that end of that video. Okay, so let's first just talk about what we know here. I'm going to do this kind of slowly. So we're going to start off by saying, oops, I have to cheat. If I don't cheat, I don't draw this well. Okay, so I have a circle centered at the coordinate plane's origin, right? So center of the circle is the origin of the coordinate plane, called a unit circle, okay? So here's what I already know about this. I know that this is 0, and this is 180, and this is 360. I know this is 0, and this is pi, and this is 2 pi. And up here is pi over 2, and down here is 3 pi over 2. Right? I don't know why I wrote it down there instead of right there. Whatever. Okay, so here's what I'm going to do. I'm going to figure out my sine of each of these areas. So sine at 0 before I start. Well, the sine function, right, if I did start, would be a triangle, right? And again, I'm going to fake it here. This is, we fake a triangle. Okay, so I'm going to say, what if I did have a triangle that just came out here, or an angle that came out here, and I fake a triangle, right? So then this would be my theta, and this would be my opposite, and this would be my adjacent, and there's my hypotenuse, right? Okay, so the sine would always be opposite over hypotenuse. So it's always going to be the y value. So if I'm sitting right here and I didn't go anywhere, my y value is 0. So sine of 0 is 0, right? And that's 0 radians or 0 degrees. It doesn't matter. It's 0. Okay, what if I moved over to sine of pi over 2? So rotate it up here and I stopped. So it's sine of pi over 2. Again, I'm sort of faking my triangle, but it's the y value that's always the sine. What's the y value here? 1, because that's the radius. So this is 1. Okay, I'm going to keep going. Sine of pi. So now I'm over here, right? Okay, I'm over here. So again, my y value is 0. I'm not moving in the y direction. And sine of 3 pi over 2. So that's, and then down here. So this is sine of 3 pi over 2. My y value is -1. And last one, sine of 2 pi. I come back up here, and again, my sine value is 0. Okay, now I'm going to use this information. Get another piece of paper. I'm going to use this information to graph on a horizontal graph. Okay, and that might seem weird, but again, when you watch this other video, you'll see they have a good picture of what we're doing is unwrapping the circle and making it go along the x-axis. Okay, that's basically what's happening. So this is the sine curve, basic sine curve. Okay, so x-axis, right? We're taking the circle that was here and we're unwrapping it, kind of like we're cutting it right here and we're unwrapping it and laying it down this way. Okay, so we're going to mark up this diagram. Okay, all the way around, one revolution is 2 pi, right? When I go halfway, I'm just eyeballing, that's pi. When I go half of that, that's pi over 2. And if I'm counting by halves, this is 3 pi over 2. Okay, I'm going up as high as 1 and down as low as -1. This distance doesn't really matter how far I'm going. It's just a unit in this case. Okay, so I'm taking these values. When I'm at 0 degrees or radians, it's the same here, then my sine function is at 0. When I'm at pi over 2 radians, my sine function is at 1. When I'm at pi radians, my sine function's back to 0. When I'm at 3 pi over 2 radians, my sine function is down at -1. And when I'm at 2 pi, my sine function is at 0 again. So this curve does this. And in theory, it keeps doing that. Right? So it just keeps going. Okay? But that's one full cycle. One period is what that's called. Okay? We'll talk more about that in a minute. Okay. Now I'm going to do the same thing for cosine. Okay, so I'm coming back over here and I'm going to talk about cosine. All right, so cosine of 0, well, the cosine, again, would be adjacent over hypotenuse. So this is actually the x value. And my x value here would be 1. Cosine of pi over 2. So up here, my x value is 0. Cosine at pi, my x value is -1. Cosine of 3 pi over 2, that's down here, my x value is 0. And cosine of 2 pi, back over here, my x value is 1 again. Okay, so watch when I graph this. Okay, so when I graph this guy, very similar. Okay, so I'm going to mark up this diagram. Here's 2 pi, here's pi, here's pi over 2, 1 half, 2 halves, 3 halves, 4 halves, right? -1 half pi. Okay, and I'm going to go up to 1 and down to -1, okay? And let's follow this. Cosine of 0 is 1. So this one starts up here. And then cosine of pi over 2 is 0. And cosine of pi is -1. That's down here. cosine of 3 pi over 2 is 0, and cosine of 2 pi is 1 again. So this one actually goes like this. It's challenging to not make it look like a V because it's a curve. And again, if it continued on, it would go like this, right? Continuing on. Okay, so this is one period of the cosine curve. So what I want you to try to realize here is that they're really the same curve, right? What happened is, if you can picture, right? So this is just, it just keeps going. If you can picture taking this axis and moving it over a half a unit, so it's here, now you've got the cosine curve. See that? So the cosine curve is really the sine curve just shifted over a half a unit. Okay, cosine curves start on the y-axis at the value of the height or the amplitude, and sine curves start at the origin. Okay. We can't always tell from a picture if we're looking at a sine curve or a cosine curve, because how do we know that this is really a sine curve and not a cosine curve that's been shifted? We don't know. So technically they have to tell us, okay? They have to give us that information. Okay, so now we're going to talk about, hold on. We're going to talk about the way that they write this equation, right, with symbols. And I'm going to talk about your textbook, and then I'm going to tell you to look at an old video and show you that it does it a little bit differently. So this is the whole thing. Y equals A sine parentheses bx minus c, close the parentheses, plus d. Okay. Now, there's a number of things that go on here. You have to watch for B. B is going to be important. And usually before you start to try to manipulate this equation and figure out what the translations are, you're going to want to factor out the B, which means factor it out of B and C, right? So let's say, for instance, if B was 1, then we don't have to do anything. But if B was 2, we would have to take C over 2, right, and factor out this 2, so it would come out like over here. So we would have B times x minus c over b, right? Okay, so I'm just going to make a little note of that. Factor out b. Okay, now we have to talk about what these all stand for. Okay, some of this is really easy, and again, when you look at the next video, you're going to see how easy this is. Okay, so the first thing is the A. A stands for amplitude. Amplitude is simply a height. So for instance, in both of these, right, I didn't label this, sorry, this one's cosine theta. Okay, in both of these, the amplitude was 1 because A was 1. Well, if it was -1, we would have flipped it upside down. So this one would have gone down first and then up and then down. And this one would have started out at -1 and gone up and then down and ended up down here. Okay, so that's just flipping it over the x-axis, what we've been doing with all transformations. So very often they talk about this as the absolute value of A, right? Because the amplitude goes at, like, the same distance both directions. So it tells you how high you're going, but it also tells you how low you're going. So if you want to put absolute value around that, that's fine. Okay. The other thing is your textbook refers to this as a midline. They're like, find your midline. So in other words, what they mean is if your whole graph shifted up, you still have to find where the axis would have been, right? If your whole graph shifted up or down, you still have to find where the whole graph would have been, where the x-axis would have been, had you graphed it just without that shift. So that's called a midline, okay? The next part here is the B, and the B is about stretch or compression. That's really difficult to manipulate. So we're not going to really worry about what that looks like on a graph so much. But again, it means this thing is getting skinnier or it's getting wider, right? Okay, so it's spreading out or it's getting skinnier within this same period. But really, that is really more dependent on the period, which we're going to talk about in one more second. Okay. The C is just what it is everywhere else, right? The C is, because it's attached to your X, is your horizontal shift, if it's shifting left or right. C is your horizontal shift, okay? But they also call this a phase shift, okay? So just because they want to be fancier in pre-calculus, instead of saying, oh, it's a horizontal shift, now they're saying, oh, we're getting more sophisticated, we're going to give it a new name. Phase shift, same thing, okay? All right, and then the last piece is D, which again, very common, that's your vertical shift, up or down, okay? All right, so those pieces should make sense, I hope. And here comes the piece that they didn't talk about, and it's really important. It's the 2 pi over b is the period. Okay, what does period mean? Period means how long does this take to do one complete cycle? Okay, in standard form, right, the parent function of sine theta or cosine theta takes till 2 pi, right, one full revolution to do a full cycle. But in shifting things, it might do the whole full cycle in pi units, or it might only do half a cycle in 2 pi units, right? So we have to know that, and the way we find it is by doing 2 pi, a full cycle, over b, the thing that we had to factor out at the beginning, okay? So this really means how long to complete one cycle. Okay, the other thing is on the homework, they ask you to graph some stuff, and they say graph 2 cycles. I think 1 cycle is enough. I don't think you need to really graph 2 cycles, but if you want to do 2 cycles, you certainly can. So I'm going to suggest that you watch an older video, and in the older video, the only difference here is this. I'm not even going to write the whole thing, because in the other video, oh, you can't even see the yellow. In the older video, they do that, okay? And they might have parentheses around that. So it's before we did the subtracting the C or adding the D. And different letters were used there, I think. I can't remember what we used because it's not in the video. The video doesn't talk about all of this shifting stuff, okay? But the shifting stuff is stuff you already know, so it shouldn't be that bad. The worst part of the shifting stuff is that you have to factor out the B. So as long as you remember to factor out the B, you're going to be fine here, okay? But again, watch that other video because it's going to really help you figure this out, okay? So instead of B, it's called K, and they're lowercase in the other video. Okay, so I'm going to ask you to watch an older video. I'm going to post this and put up the assignment, and I hope we'll be okay. Okay, keep in touch with me. Let me know how everything's doing. Have a good night.